Hi everybody. Today we're going to be doing Boids simulation in Raylib. It's a pretty simple kind of looking thing. Not looking, but it actually looks awesome. But it's pretty simple actually to implement to be able to get this kind of behavior. It relies on coherence, separation, and alignment, and visual range, and a couple other factors which we can tune. In this simulation from Ben Eater, he did some cool things where like he allowed you to decide it on the slider so you can kind of see what it looks like in terms of whether there's alignment on or whether it's all the way off. We're not going to be doing that. We're just going to be implementing a basic simulation with Raylib. And so yeah, let's get to it. So I'm going to start by making the project, and I'm going to use this thing I actually recently made, which is called Go Test. I'm thinking about making like a video on how you can actually make it. It's online on GitHub. You can use it if you want. It's not completely done, but it's also not wholly original. It's based off someone else's project called Try, and it's the exact same thing. It's just basically like a little project manager for little test projects. So we're gonna do like CPP Boid, and then we'll go into CPP Boid. So then we'll do set dot. We'll open it up. It opened up into the wrong thing, so let's put it there. So now we have Z, and everything's looking good. Cool. So what we're going to do is we're going to do new folder, src. We're also going to make a new file, c make list.txt. And I'm just going to copy and paste stuff into here. And basically all this is really doing for us is it's getting Raylib and it's putting it into our build thing. So now I'm going to make another folder called build. We'll come back to that in a second. We need something here. So we'll start with just like, we'll go to like Raylib, right? And Raylib, they have like a nice little like test program so you can see that it's actually working. And you can actually see like the, so cd build, cmake, I think all I have to do is this. Yeah. So now it's built stuff. And now if we like resave, I think this will actually just work. Cmake, the exact command is, yeah, over there. I want this terminal just a little bit bigger. So it's build dot. So now if we run it now, you'll see like the bindings for, bindings is the wrong word, but the, where is it? Compile commands is now set up so that way Clang is going to find it on the language server and everything will just work. So if we run cpp Boid, you can see, congratulations, you've created your first window. Awesome. So we're going. So yeah, this is what I want. I want this over here. Love a window manager at some point. But that is for another day. All right. So let's get into actually implementing Boids. And you can see that Raylib has this kind of style defaulted where like the brackets are on the next line. So I'm actually just going to be following that going forward. It adds a little bit more space. It's a little bit better. So Boids will be our title. We're going to start with screen size const int screen size, and we're just going to make it 800 by 800 for simplicity, because we're not going to be using triangles. We're going to be using circles for rendering, and that's going to let us basically make everything a little bit easier. Let's actually make it like 720 for 720p. Okay, so let's start with our Boids. So we have our Boid. Nope. Boid like this, right? This is our Boid. And basically all we need to be able to make this work is we need a vector 2, and we need their position in the world. And the other thing we need is their velocity in the world. And we're going to have a big array of these. And I want to be able to define with constants how many Boids there are. So I'm going to call this std size t num Boids. And I'm just going to start with like 10 or 100, let's say. And then we can always add more when we want more. And I'm also going to take one other thing that's going to be relevant. So this is going to be like our, we'll make these like our, is there like the, okay, whatever, that is okay. So we'll have, these are like our constants, right? So I'll make like just a big comment, so everything's kind of nicely separated. Constants. Then we'll have like helper. We'll just make it like utilities, right? And the two utilities we're gonna need is this, and we're also gonna need one more. Inline float, decimal, no except, and this is actually from, we want it like this to be structured like that. And then the actual thing is we're just gonna be returning a float decimal, right? So we're gonna take rand of this, and we actually need to get that in a second. And then it's also going to be another float, and then rand max. Do this, and because we're doing a what's it called? A random. One thing you should remember is we need to cast it at some. We not need to cast it. We need to seed it, and basically this means like we're going to get actually somewhat random behavior. It is pseudo random, but that's okay. So now we have like some random number generation. And since we're already here, if you recall from like the Ben Eater video, or not video, simulation, there were a couple things going on where basically he had 3 different parameters that were basically adjustable. We're not going to make them adjustable. So separation factor is equal to 0.2f, and we'll play with this when we get there. Alignment factor is equal to 0.5f. We're not going to use these for right now, but that is okay. We're just going to put them in there, and then we'll come back to it. And then cohesion factor is equal to 0.5f as well. We'll just start with this, and then we'll just start with all 0.5f, and we'll just play with it as we go. So those are our constants. Those are our utilities. And then this is going to be the simulation. Cool. Is there anything else I want? I'm actually going to take in a few more constants just so it's a little easier and I don't have to type it out. So this is the void radius. Since we're doing a circle, right, that's basically going to be the size of the void. The diameter is just times 2 the diameter. And then I have these other 2 things, and this is going to be what we're searching for in terms of things near us versus things not near us. And again, this is basically related to that vision thing that we were playing with, but one of the things that's happening here is this is, let's say this is a barrier, this is a barrier, this is a barrier, right? And this is our void. So I think that's about right, right? So this is basically going to be, so this is our void. We're not going to look for entities super close to us, but we are going to look for entities within this range. So basically, in this, we're going to reduce this actually a little bit to like 5. So if they're within 5 of each other, or 25, because it's squared, right, it's going to say there's nothing there. And if they're within 144 of us, though, we're going to say this is there. And we're going to use that when we're calculating separation alignment and cohesion factor. Nope, thought I was going to sneeze. All that means is I have a sneeze coming later. Cool. Okay, so there's our voids, and now what we need to do is we actually need to get into the simulation. So first thing we need is voids, our array of voids. Now voids, pretty easy. Another way you could do is like std array, and then you wouldn't need to have this thing around. You could just call size, but it's a little cleaner. And then we're gonna have std size t I and j. Those are 2 indexes that we're just going to have, right? And we're going to use it throughout the program for I is equal to 0, I less than, oops. Now what we're doing is we're actually going to basically take these and we're going to initialize them with stuff that's relevant. So voids, yeah, this is fine. I dot position. Did I mess up? Oh, I messed this up. Voids I dot position is equal to dot x is equal to decimal times screen size, and dot y is equal to decimal times screen size. There we go. And then now we're initializing the velocity next, dot velocity. So this basically said you can be anywhere on the screen size. And then for the velocity, we're going to be doing something pretty similar, is equal to decimal, right, times 40 minus 20. We'll play with this. I already implemented this off camera just so I wouldn't waste any of our time. 20.f minus 20.f. So this is basically saying it can be in range of negative 20 to 20. All right, and then dot y is equal to decimal times 40 dot f minus 20 dot f. Do that. Oops. I don't need this open anymore, actually. I've noticed recently I've been typing a lot of semicolons instead of colons. But anyway, so this is going to be initialize Boids. Pretty simple. And now basically what we're going to do is we're going to get to actually drawing it. So let's start with drawing. And that's pretty easy, which is always good. I'm going to change the background because I just like a dark background in this kind of context. And so we'll have for I is equal to 0, I less than, no, Boids, plus plus I, easy enough. And then, oops, we're doing this style. We're going to get const Boid. So this is like, in the other one we had like a render thing where we were doing it. This is just by itself because it's a very simple program. Boids I, and then we can do draw a circle, right? And we can do b dot position. Actually, I'm going to do it like this: b dot position dot x, b dot position dot y, Boid radius, and then we'll do ray white. Why not? And then we can do this. There we go. Is there a problem? Oh, it doesn't like the extra comma. In Go, you do extra commas for like that new line, and I'm just very used to it now. Anyways, so there we go. Let's try and run it. CMake build, CPP Boid, and we have an error. Working directory bus error 10. All right, hi everybody. So basically the problem was it's right here. I was using J instead of I, and that created the bug. So now if we do it without rendering at all, we're good. And oops, there we go. And now if we do this, and we're rendering the circles properly, or our Boids in this case. Cool. So that works. Now we can actually get to implementing the rest of it. So this is render. This is simulate. So we start by getting the, actually I always forget to do this. Let me make this a little bit bigger so it's a little easier for you to read. Float dt is equal to get frame time. This stands for delta time. This is the time between frames, basically from the last time we drew. And then what we need to do is I is equal to 0, I is less than equal to num Boids, plus plus I. And we're going to do this, this. And now what we're going to do is we're going to get the Boid that we're working on. So Boid, B is equal to Boids I. And once we have that, there's a couple things we need to actually set up for. The first is we need the number of neighboring Boids that we're going to find, and we're going to find them in just a second. And the second is I'm going to create 3 vectors. I'm going to name it separation, which is equal to 0, 0. I'm going to name this one sum velocity, and it's also just going to be initialized to 0. Vector 2, sum position, is equal to 0, 0. There we go. So now what we're going to do is we're going to look for the number of Boids that are around us. And we're not going to look for them in the most efficient way. We're going to just loop through all of our Boids. So this is going to be like O of n squared in the most traditional way. There are better ways to look for collisions. We could look into sweep and prune. We could look into quad trees. And I'm sure there are other ways, since we're using circles, where we could make it even that much more clever. In our case, we don't need to worry about it. This is not going to be that computationally expensive, especially because we're not going crazy in the number of voids we're simulating. So it should just be totally fine. So what we're going to do is we're going to look through this, and we're going to make sure that I is not equal to j, because we're not actually interested in letting the simulation be affected by other voids, but we're going to find this other voids j, right? And then what we're going to do first is we're going to get the float distance, and we're going to actually make it distance squared is equal to vector 2 data distance. Oh, I need ray math. Oops. Include ray math. Cool, cool, cool. Let's go back to here, distance. So now we actually have it. So this can be b dot position. This is the one we're currently at, and this is the other dot position. That's the distance, right? And then what we can do is we can say if distance squared is less than Boids search separation radius squared. So this is the one where it's close to us. And if that's the case, in terms of separation, that means we're going to be trying, the Boid that is going to be trying to move away from the other Boid. So the way we're going to calculate that, dot x plus equals b dot position dot x minus other dot position dot x. And then we can do this, y, y, y. So that's separation calculated. We'll come back to actually using it in just a second. Actually, you know what? I think I'm overcomplicating this right now. Let's actually, let me put this in. Distance squared is less than void search visible radius squared. So I'm going to not even populate this right now. All I'm going to do is I'm going to actually update this one thing, because I'm realizing I'm going just way too fast. So b dot position dot x plus equals b dot velocity dot x times dt. B dot position dot y plus equals b dot velocity dot y times dt. So all this is doing right now is we're just running a simulation where we have applied the velocity, and we're seeing that if it's actually going to work. So we do this, we run it, and you can see all of a sudden things are moving around. We don't have any acceleration, so that's why it's not getting progressively faster. But you can see overall this is working. You can also see that the Boids will run off the screen at a certain point, and we're actually going to fix that at some point. We'll actually fix it right now. Let's do that. So I'm not going to make it so if they start to get to the end of the screen, they're going to start to move back. Instead, what I'm going to do is I'm going to have them start to, if they go to this side of the screen and over, I'm going to put them over here. If they go over here, they're going to go over here. So the way we can do that is if b dot position dot x plus Boid. Is it plus? I'm going to just do it like this. It's not perfect, but that's okay. If it's less than 0, the position is less than 0, we say b dot position dot x equals screen size minus Boid diameter. So if they go over this way, we're going to put them over here, and then we're going to move them over a little bit. Okay. Else if b, oh, I don't know why I did that, position dot x is greater than screen size, b dot position dot x is equal to Boid diameter. So this is basically saying if they go over this, they're going to be moved to 0, but we're going to push them over so that way they're fully rendered. And then I'm going to format this so it's just a little more pleasant to read. And this actually is going to be the exact same now when we get to y. So now we're doing the top and the bottom. But instead of being x, we're going to make it y. And it's all the same. So now if we run this, you'll see like, let's see. It is a little bit weird because it seems to not go over this side. Like this one will be coming here and they come here, but I would expect them to be, so where did I mess up? If b dot position dot y is greater than, where's my window writer? There it is. There we go. So now I do it, and you can see it goes over. We'll look at this one real quick, and it's going to go there, and it just popped up over there. If we go to this one right here, it's there, and now it's over there, moving this way. So now we have that working where it's going to kind of like loop around the screen. So now we can actually get back into implementing all this stuff. All right, cool. So now what we're doing is we're going to do alignment and cohesion. So basically this is if distance squared is less than the search radius. And what we're going to do is we're going to first do our neighboring Boids plus plus. And then we're going to update our sum velocity. So this is the sum of the velocity of the Boids that are around us that we can see. Velocity.x. X. Oops, we want to do like this, 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 ry, ry. And in the other case, we have our sum position. Let me put it like sum position, and then it's dot x plus equals other dot position dot x sum position dot y plus equals other dot position dot y. And now that looks good to me. Now we're not actually doing anything with that yet, but we can get to it. So the first thing we're going to do is we're going to update our velocity based on separation. This is easy enough. B dot velocity dot x plus equals separation dot x times separation factor. Right? And then we just need to do this twice for y. The next thing to do is update based on alignment and cohesion, and we're going to use our neighboring Boids here. Is greater than 0, right? And we have alignment, and we have cohesion. Cool. So b dot velocity dot x plus equals, and I'm going to come back to that. I just want one line there. Cool. So we have our sum velocity.x divided by neighboring Boids. Simple enough. And then we're going to do minus b dot velocity.x. I'm going to change this to be below it. I think it's supposed to be below it now that I see that. Update position. Okay. B dot velocity.x, alignment factor. And is there anything else there that I'm missing? B dot velocity, so basically what we do is we take the velocities of the neighboring Boids, but we take the average of it. So this is our average, and then we minus our current velocity, and this is kind of like aligning where we are. Okay, cool. And then what we can do is we can do this again one more time, but this time we need to do it for our y, y, and y. This one is also going to be exactly the same, but instead of using this, it's going to be the sum of the positions. So, and that's all that is. And then we update it. And then the other thing we need to do is we have this big velocity, which could be 0, it could be something huge. And basically what we want to do before we actually update everything is we want to make sure the velocity isn't getting like too massive or too small. So vector 2, if I could type clamp value. So we're just clamping the value in between the magnitude. B dot velocity, and I'm going to say like 20f and 100f. And I think that is actually all we need to make this work. And you can see we have some stuff happening where everything seems to be going like the exact way. So it's not quite what we want. So we can play around with it just a little bit. The first thing is I've never liked like a high separation factor, so I'm just gonna like reduce that. I think it's cooler when they like kind of like move away from each other. The next thing is you can kind of see like, let's see, not quite right. I don't like how it keeps switching to that, but that's okay. I can play with the original value I had. Still not loving that. Let's go into here, because I did, in like the original implementation I had this like this. Don't love it. It's a little better, but it doesn't really make a difference. Okay. Let's see what happens if I don't have this. And you can actually see why we want a, why we care about clamping the value so it doesn't get like too massive. Otherwise, I definitely have a little bug here. And this is one of the bugs. This should be position. That makes way more sense. And the alignment and cohesion, yeah, we want to do that before that, and then we'll update that. Let's see. So right now, everything is just like, you can see how everything, that was actually better because everything like kind of really came into each other that time. Let's make this a little bit bigger. Let's make this like 2. Let's see what we get. And you get like very jittery movement right now. I'm gonna say that these are just like too big. Let's make this like 5. That looks a little bit better. We'll make this like 10 by 10. We're looking better now. You can see the separation is like too large almost, because like we get this like perfect little like triangle thing. But let's see if I'm making any other obvious mistakes. 10 by 10, 12 by 20. And then like we have like this search separation radius, visible radius. I want to see if there's like something I can do to just make it a little bit prettier. I'm fine with that. We reset neighboring Boids every time. Separation is fine. I obviously would rather have it like separated out a little bit so it's easier to read like that, but that's meaningless in terms of changes. B dot velocity, separation dot x, separation dot y, times the separation factor. I'm going to put this above one more time just to see what we get when it's like this. And that's actually not bad looking when we have it like that ordered. You can see they kind of get like super close to each other and like get stuck on each other. But one thing we can do, just to always see if like this looks better, we can like just make it bigger. Like if we have 10,000, I don't know how laggy, that's just too much. Let's do like 1,000. But yeah, I don't like how they're like so obviously close to each other. So let's go into here and see if I had a little mistake here. So we have Boids J, distance squared, but otherwise it shouldn't actually be other dot. So if I is equal to J, we don't do it. If distance squared, B dot position, other dot position. It's j. We're skipping if I is equal to j. It just seems like they're coming so close to each other so quickly, like they're all like condensing on that 0, 0. And this isn't 0, 0, this is 0, 0, but on the origin. And then we get this like kind of like odd behavior. So let me go away for one more second and figure out exactly what's wrong. All right, so I'm back. Sorry about that. So nothing was actually wrong per se. It was just the configuration wasn't very good. So basically this search radius was just way too big. So I put this down to like 6 or to like 5 by 5. If we do like something like this, for example, this is probably fine too, but you can see that they really like glob onto each other pretty quickly. So I think 5 by 5 is the answer. And then I made the separation radius a lot smaller. It was originally like 5 or something. And then also what I did was I upped the separation factor by a good bit. If I have it like 0.2, for example, like this, then you can see like everything like globs onto each other such that like they look like they're like almost in each other. Like some of them will just like connect pretty, yeah, like, and I don't love that. So I think a little bit of we can make it 0.5 even. And then we have this. Let's make this a little bit bigger. Let's see if we can even handle that much. Right. So this is about the limits where you can really see like it looks awesome. It looks awesome, but it is very laggy. So let's make it like 2000. That'll be totally fine. And so you can kind of see like 2000 is a good limit for like how many boids we can have on the screen at once without there being any issues. The one issue with Y, like, and you get yeah, this is exactly what we want. I think the separation should be a little bit bigger actually. So let's make it like this. And I think if we make this like a lot bigger, yeah. So now like they come on to each other and then we get this nice little thing and we can get like really fun behavior where they're with each other for a little bit and then they're gonna like kind of like separate and make their own little flocks for a little bit. And you can see there's like some brief alignment and then they're kind of pulling away from each other. Then we connect and then these ones at some point are gonna like disconnect if things go well. No, so far they're just like a very cohesive flock. Yeah, there we go. So we get like some disconnection there. I think we can even make this like a little bit more. Make this like 1, and then cohesion will like lower it a decent bit. Because that I kind of personally like when they're like, when they kind of separate from each other. And they're kind of like everything's its own flock. It also doesn't look like they're 1500 different voids in the screen, to be totally frank. So let's make, so let's make that like very pronounced. And now we're really getting what I think is a decent looking simulation. But yeah, this is Boids. It's just 3 rules: cohesion, separation, alignment. Cohesion is where they're coming together based on their positions. Alignment is where the velocities are like matching each other, and separation is when they get too close, they want to push away from each other and go in the opposite direction. And yeah, it's pretty simple. I hope you enjoyed watching this video. Didn't go as smoothly as I would have liked, but yeah, I'll see you in the next one. I was thinking of doing like a quick little lightning simulation video. We'll fix this. And if anybody wants the source code, I'll have a link to like a GitHub gist at the in the description, and maybe like up here at the top right if possible. I don't really know exactly how to do that, but I will figure it out. And yeah, I hope you have a good one. Bye, everybody.